Wondered how a power plant's output changes with the weather? I just built a machine learning model to find out. In this project, I tackled a classic data science challenge: predicting the hourly energy output of a combined cycle power plant. I used a dataset with over 9,500 hourly records. The goal? To predict the exact amount of electricity generated, measured megawatts, using just 4 key environmental factors: the temperature, ambient pressure, relative humidity, and the exhaust vacuum. Since we're predicting a specific number, this is a supervised regression problem. Think of it like this: my model learns the relationship between the weather and energy production. This could be a game changer for power plants, helping them forecast their output and plan operations more efficiently. Let's dive into how I built it and see the results. Homed. Hey everyone, diving into some data science today. When you're building a model, how do you know if it's actually any good? Let's talk about performance evaluation. For my project predicting power output, I went with mean absolute error, or MEI. Why MEI? It's super intuitive. It tells you the average error in the exact units you're predicting. So, a MEI of 3 means my predictions are off by an average of 3 megawatts. Simple, right? Now, to avoid tricking myself into thinking my model is better than it is, I split my data. I took 80% for training and kept a separate 20% as a final test set, completely untouched. Then, within that training data, I used 5-fold cross-analysis technique, helps compare different models robustly and seriously, cuts down the risk of overfitting. It's a crucial step for building a reliable model. Ever wondered which model to pick for your data science project? Let's break it down with a classic face-off: linear regression versus random forest. First up, I built a linear regression model. Think of this as our reliable baseline. It's straightforward, easy to understand, and you'd be surprised how often it gets the job done. It's great at finding simple, straight-line relationships in your data. But what if the relationships aren't so simple? That's where random forest comes in. This powerhouse model can uncover complex, non-linear patterns and interactions between your features that linear models just can't see. So, how did they stack up? I used cross-validation and compared them on mean absolute error. The winner, the random forest model, consistently had a lower error. This means it did a much better job of understanding the real structure of the data. Because of its superior performance, I chose random forest as my final model. So, how did we make sure our final energy prediction model was actually good? It's all about a clean, unbiased test. After using a method called cross-validation to pick the winning model, we retrained it on all our training data. Then, for the grand finale, we tested it just once on a brand new, completely untouched test set, 2. This is super important because it shows us how the model will perform in the real world with data it's never seen before. The results. Our model had a mean absolute error of around X megawatts, which is pretty accurate, and an R-squared value of X. This means it explains a huge chunk of why energy output varies. What's really cool is that the model revealed the most important factors are temperature and exhaust vacuum. This confirms just how critical thermal conditions are for plant efficiency. Ultimately, we've built a powerful tool that can really help with forecasting and optimizing energy production. Thanks for watching, and don't forget to like and subscribe for more data science insights.